We're now going to move to the sort of final stages of parallel streams and begin the discussion of how results are combined and the control you can have over how the results are combined. So we'll first here start by talking about how reductions are performed to combine partial results into a single result in a parallel stream. So we've talked about in conventional sequential streams before, but that's pretty easy. Parallel streams are much more interesting. So as the common fork join pool finishes processing chunks in the ways we just talked about, these partial results are then joined together to provide a final result, a single final result, but it's done in a piecewise manner depending on what kind of collector you use. For this discussion right here, we're going to assume we're using a so-called non-concurrent collector. I'll talk about concurrent collectors later. And so what's going to happen is as these partial results get complete, they are joined together successfully, or successively, hopefully successfully too, to produce a single final result. The join that occurs in a non-concurrent collector always happens in a single thread, the parent. So if you've got, let's say you've got two children threads, then here's the parent, and this joining takes place in the context of the parent. And that's significant because we never have to worry about race conditions. There's no need to deal with locking for non-concurrent collectors because it's not trying to join things or merge them together in multiple threads. It's going to join them only in a single thread. So there's never a need to worry about synchronization in this case. Now, what's interesting about this is that different terminal operations, namely collect versus reduce, combine their partial results in different ways. And we'll see that this is also important when we deal with different kinds of collectors as well, because there's concurrent collectors and non-concurrent collectors. We'll talk about that next. What I want to talk about now, though, is the difference between reduce and collect. So they both end up creating reduced results, results that are a single thing from merging a bunch of things. Reduce, however, always works by creating new immutable values out of existing immutable values. So that's what reduce does. And here's an example of this. Let's assume, for sake of argument, we've got a stream that looks like this. We're going to end up with a range of long primitives from 1 to n, and then in parallel, we're going to reduce these things. And this is just an example of that reduction. So the way this works is we start out with a range of longs from 1 to 8. That gets subdivided by the splitterator up into 2 ranges of, say, 1 to 4 and 5 to 8. And then that gets split up into ranges of 1 to 2, 3 to 4, 5 to 6, and 7 to 8. And it actually gets done even further, but let's stop at that point because otherwise it gets a little silly. So as you can see here, longs of 1 to 2 are processed sequentially, and the way they're processed is by multiplying the two values together to create a single reduced result. So obviously, what's going to happen here is we're going to end up saying, we'll end up seeing what we're going to do here in a second. So 1 times 2 is going to yield a result, 3 times 4 is going to yield a result, 5 times 6 will yield a result, 7 times 8 will yield a result. And you can see what those results are. So 2, 12, 30, 56. Those are the things that might be done, say, sequentially. And then what we're going to do, or what the framework is going to do for us, is it's going to go ahead and apply this lambda expression. And this is part of the reduce phase. So this is the map phase here. And now we're going to do the reduce phase. And the reduce phase is going to take each pair of values and multiply them together to provide yet another immutable reduced value. So obviously, no surprise, 2 times 12 is 24, so that's the reduction here. 30 times 56 is 1,680, probably not quite as obvious to you, unless you're a math savant. And then the final thing that'll happen here is we're going to reduce, once again, 24 times 1,680, which will yield 40,320. And so those reductions are done in parallel, but they're always done in a way where we don't have to worry about any side effects because we're producing immutable values, primitives. So we end up with a single result when we're done. Gavin. They'll get run in every reduce. So the question is, how do the reduces get run? A given reduce always runs in a single thread, but it's not the same single thread. So we could have this reduction done in one thread. This reduction could be done in a different thread. So the reduction of 2 and 12 could be done in one thread in parallel with the reduction of 30 and 56 in a different thread. So the actual reduction is done in one thread of any given pairwise set of elements, but reductions of multiple partial results can be done in parallel, thereby giving you the speed up. And then ultimately, and this reduction could be done in yet another thread. So when the reductions happen, the reductions can happen in parallel, but at any given point in time, any two values are reduced in a single thread. And you'll see some examples when we look at some code later. So that's reduce. Reduce works on immutable values. It takes immutable values and it creates a reduced immutable value. And that happens over and over again until you have a single result left. Collect, in contrast, mutates an existing value. If you think about what collectors do, they work on these so-called mutable result containers. And we'll look at that more in a second. So they're mutable. They can be changed. They're malleable, like Play-Doh. And here's a simple example of this. So I don't break this down quite as comprehensively as the reducing of the multiplications of the factorial, because it would take a lot more slides than I have here. But basically, let's say we have all the words in the works of Shakespeare. So here's the program snippet, which you can get from my EX14 example. You look at all the works of Shakespeare, and you split them up into the words. And what we're trying to create here, by the way, are the unique words in Shakespeare. So we start out with all the words in Shakespeare, and then in our parallel stream, that'll get split up into the first half of the words in Shakespeare and the second half of the words in Shakespeare, and then the first quarter of words in Shakespeare, the second quarter of words in Shakespeare, and this could continue on and on and on until we ended up with, atomic level words. And then what we're going to do, in this particular example, maybe we're searching, who knows, we're doing something. But at the very least, what we're going to do is we're going to collect the results together. And here's what we're going to do. We're going to collect the results together into a tree set. Remember, a tree set is a set that contains no duplicates. So, of course, we're going to end up with the unique words of Shakespeare by putting all the results into the tree set. So what's going to happen here is these things come together. We're going to take the first quarter of words and the second quarter of words. And of course, I'm skipping some decompositions here just to make it fit on one slide. And we're going to collect them together. And we're going to take, the first quarter of words and the second quarter of words. We're going to collect them together into a mutable result container that contains the unique words in the first half of the words of Shakespeare. And then over here, we're going to take, again, without loss of generality, we're going to take the third quarter set of words, or it's not set of words, the third quarter collection of words, and the fourth quarter collection of words, and then we're going to collect them together, and we'll end up with a single mutable result container that contains the second half of the words of Shakespeare that are unique. And then the final thing that'll happen here, and both of these reductions, of course, could go on in different threads, although any single reduction takes place in one thread. So the reduction of the first two quarters could happen in one thread. The reduction in the third and fourth quarters of the words could happen in a different thread. And then some thread will reduce to a single unique set of the words of Shakespeare. Yes, Jenna. Exactly. So the question was, what's happening here in these intermediate steps? So there will be a tree set created here. Let's call this, tree set A. And there'll be a tree set created here. And they'll both start out as empty. And this tree set A will contain the unique words of the first and second quarter of Shakespeare words. Tree set B will contain the third and fourth quarter unique sets of Shakespeare words. And those will be two distinct tree sets. And then this will come and create a final tree set, which will then take the words from tree set A, words from tree set B, and then merge them together. And of course, there could have been duplicates between those two sets. Within a given set, there wouldn't be duplicates, but there could be words that would appear in both tree set A and tree set B, and those will be merged together into a single unique set of words, which will be the final result. So the thing to keep in mind in the back of your head is there are intermediate subsets of result sets, in this case, tree sets, that are being created as we merge everything back together again. And if you think about it, I mean, it actually makes a lot of sense, right? You're working on the part you have visibility over. That gets collected into a temporary tree set. That guy on this side gets merged into another temporary tree set, and then we merge them back together. And of course, in the real example, there'd be lots more layers than I'm showing here. I just wanted to keep it simple. Did that answer your question? Okay, great. Now, so that's one way to do this. One way to do this is to merge things together. And we'll talk about this in more detail, but one of the downsides with that approach is that it's pretty expensive to merge these sets together, especially if you've got lots and lots of these intermediate mutable result containers you're merging into. Even though it's all going on in parallel, there's a lot of duplication of effort. So an alternative way to do things is to use something called a concurrent collector. And we'll talk more about concurrent collectors shortly. They are different because what happens there is that rather than merging things together into these intermediate sets with having, you know, tree set A here and tree set B here, and then you merge those into tree set C, and keep in mind that in a real situation you have lots more layers. Instead, you have a single result container, a single set, which is a concurrent set, which means that different threads can be adding stuff into it at the same time without having to worry about corruption and race conditions and so on. So if you were to use, say, a concurrent hash set collector, then all of this merging would take place on one and only one set. And that might actually be a win. And we'll talk later about when it could be a win and when it might not be a win. In practice, you'd actually have to try it out and see which one was more of a win. But really good hash sets or tree sets can make this very fast. Okay, so that's kind of a high-level overview of the differences between reduce and collect, focusing primarily on how non-concurrent collectors behave.